Yeah, thanks, Dragos, and thanks everyone for being out here. Tara is right; it's a pretty cold night, and it's wonderful to see so many people here. As I should probably explain the title slightly before I jump into it. Alex was asking me; he didn't know RBC is doing this sort of thing, and I said, well, that's actually my personal passion rather than what I do at work. As Dragos said, I'm a physicist by training, and then I turned into a data scientist. So science and machine learning are both kind of things that I'm very passionate about. And I'm very interested to see how these two interact, and I sort of try to track what's happening in that space. What I'm going to talk about is not going to be as nice and practical as the previous talk, but hopefully it gives you a few things to think about as you walk out of here. So let's talk. let's talk. The original title was Physics and Deep Learning, so I'm going to talk about that at the beginning a little, and then go into generally science and machine learning. So who here knows what Large Hadron Collider is? I didn't expect that. All right, for those of you who didn't raise your hand, click here. So Large Hadron Collider is this thing that you see here. It's literally one of the most advanced machines that human has built. And the purpose of this machine is to carry out a very interesting experiments in physics. This is a huge international collaboration. A lot of countries are investing in this and helping out to carry this out because it is ridiculously expensive and it needs a ridiculous amount of resources to build it. This is located on the border of Switzerland and France, as you can see, and it is about it is a ring that is about 17 miles in circumference. So what you see here is essentially an aerial picture of the site, but everything is happening about 100 meters underground. So it is a tube that is going around in this ring, and in this tube, what they do is that they grab protons and they accelerate these to velocities very, very close to the velocity of light. So these are like particles that are traveling as fast as light does, essentially. And then these particles collide with each other. And when they collide with each other, there's a little explosion that happens. And these are extremely energetic particles that run into each other. And when that happens, a very interesting explosion happens. We believe that sort of explosion simulates sort of the birth of the universe that we live in. So this is a very ambitious experiment in which we're trying to understand very, very early moments of the universe and how things were behaving there. And a lot of particles come out of this explosion, this collision, and we are interested in the properties of these particles that are coming out. And there are a large number of detectors around these that collect the signal from these the particles that are generated, and we are interested to know what is happening, what are the properties of these particles and things like that. So we have a large number of detectors working and generating data that we can then grab and explore. So what is the largest? So a lot of people ask me, what is the relation between physics and data science? And as an experimentalist data science, I've been working with data a lot. And these guys take data science to a different level. So like, what is the largest data set that you guys have worked with? Is it megabyte, gigabyte? At my work, we mostly work with at most like terabyte. At LHC, the Large Hadron Collider, they produce about 25 petabytes of data every year. That's a ridiculously large number. And the thing that is more interesting is that the signal they are looking for is on the order of a few megabytes. The contrast there is huge. So essentially, they're producing 25 petabytes of noise, out of which they're looking for few megabytes of signal. And that's a very, very interesting data science problem for anyone who's interested in data. Traditionally, they've been interested in studying this system only from physical principles. But given the amount of data that is coming out of this, they started thinking out of the box, then can we leverage, say, machine learning and the data science techniques that we're developing, and they're doing so well, to do a better job. So let's take a closer look at this. So that center location that you see there is essentially when the collision happens, and the tracks that you see there are essentially the particles that were generated and coming out of this explosion. And there are a lot of detectors around these, as I said, tracking exactly where these particles are going. And the trajectories are reconstructed out of this, which are what you see, and they're called jets. These jets are very interesting because looking at the properties of these jets tell us a lot about the physics that is happening in that extremely energetic collision that happened. And that's what we are interested to learn more about. So traditionally, what they do is to look at these jets, study their properties, and based on those from the first physical principles, try to understand what is happening in the collision zone. But then what they realized was that, in fact, they're only dealing with a few different types of jets. So as long as you can kind of tell what type of jet you're dealing with, you can go a long way in predicting and understanding the physics that is happening. So it is essentially a jet classification problem that we're dealing with. So they've been using things like decision trees and random forests often to draw better conclusions. But recently, in the past year, there's been a very interesting development where they started thinking about using deep learning for this. So as I said, what we're interested in really here is understanding the properties of jets, and out of them classify them to different types that we are interested to know. And given all the advancement that we have had in convolutional neural nets and their success in object detection in images, they thought, why don't we try to map out the properties of these jets in a 2D space that looks like an image, call them jet images, and then apply a convolutional neural net on it and see if we can classify these jets better. And that's exactly what they did, as you see here. Obviously, the problem here is that the images that we normally use are very dense, but these jet images are very sparse, and they had to modify the usual networks that we use to some extent. But the interesting thing is that they got an extremely better and more precise classification out of this compared to what physical principles were able to provide. And that was very, very interesting. They didn't stop there. They even wanted to use, or they did use, generative adversarial networks to create new types of jets to do experiments and simulations on them. But as physicists, the fact that this neural net is giving us better results is not going to satisfy us. So we need to understand why exactly it is doing that. Therefore, they're doing a lot of research in what these neural nets are actually doing to understand, to decipher, because I assume a lot of you know that we don't really know what deep learning does in that black box when things happen. There are a lot of people working on that. And hopefully these physicists who are trying to decipher these will be able to give back to the deep learning community because they're really interested to know how these classifiers are doing a better job than our physical intuition. And one thing to remember is that this is really augmenting our ability to understand physics better, but it's not replacing the physical intuition, at least not yet. For those of you who are interested, you can take a look at the first link. It is an open data part of the data that is coming out of CERN, and you can potentially play with it. And there are 2 competitions that they posted to study different types like Higgs boson using machine learning that you can also check out. As I said, like, physicists are very interested now, at least this subset of physicists, in explaining what these deep neural nets are doing. But they're not alone. There are other physicists who are trying to explain the high performance of deep neural nets based on first physical principles. And that's also a very interesting paper to read. Somebody, I guess Hassan, was telling me that he was hoping that I talk about quantum machine learning. But since I gave a talk about that recently, which is my area of expertise, but unfortunately I'm not going to go into it, but this paper is really good, and I'm happy to chat to you if that's what you're interested in. But physics is not the only science that is using machine learning or is having interactions with machine learning. All sciences are. Chemistry, in chemistry, for example, we are talking about discovery of drug and perfume and new material using machine learning techniques. In statistics, we are talking about things like automatic statistician or data robot, and they are very primitive now, but they're moving in the right direction at least. In astrophysics, we are using machine learning to cluster images that we have from galaxies. And in medical sciences, we're talking about things like cancer detection and personal medicine. And all these advances are great, but let's focus on biology for a moment. Biology is interesting because it is a very interesting science in a sense that even the simplest models, even the simplest model biological systems like E. coli, that is a very tiny bacteria, is extremely complicated. It has like thousands of genes and proteins and small molecules that are interacting in space and time. And even if you grab all the PhDs in the world and put them in a room and ask them to decipher that, it's not going to be possible. So we need another way to deal with this problem. So let's step back and think about how we do scientific discovery. The way it usually happens is that we start from some background knowledge. It exists in the form of scientific papers right now. We read a lot of scientific papers. Then we come up with a new hypothesis. We create an experiment out of that hypothesis. We carry out the experiment. We get some data. We analyze it. And then it either results in a new hypothesis that we need to test or a new theory that we added to the background knowledge. It's a very complex process, but it looks simple when you think about it like this. It's a fairly repetitive process. So maybe, like many other repetitive processes, we can make this automatic as well. That's exactly what a group of biologists in the UK tried to do. They created Adam. Adam had one task. It was to determine the function of a certain gene by a series of growth experiments. So what they did is they had that exact cycle of discovery that I just talked about, but they added a robot to the system to carry out parts of this experiment. So essentially what Adam does is that it grabs the background knowledge, it creates a knowledge graph out of it. A knowledge graph is, you can imagine it something like a graph where the nodes are concepts that exist in the particular science you're thinking about. And the connection between nodes are how those concepts are connected to each other. Like there could be two concepts in a science that they don't really talk to each other. They're not related, so there is no connection. But there could be two concepts that are very related and they could be connected. So essentially, if you step back and think about it, science is not a lot more than a bunch of concepts and how they are related to each other. And that's exactly what Adam starts from. It starts from a simple graph that has a lot of different concepts in it and how they are connected. The next step is to infer a new hypothesis. A new hypothesis can be a new node or a new connection. And we're already doing that in social media analysis. We have social media graphs, and we predict that, oh, I think there should be an edge here. So here's a Facebook friend recommendation. Here's a LinkedIn connection recommendation. So that's not exactly, that's very similar to what Adam does at that step. The next step is to design an experiment. And of course, this experiment has limitations by the time and space and the machinery that exists, but it also tries to optimize cost and time to be able to carry them out. And in the next step, there are videos on YouTube of this machine in action. So I recommend you look at it. It is interesting. You can't see a lot, but it's interesting to see it doing it. And at the end of the day, it carries out experiments, it grabs the data, and uses machine learning to interpret the results. And that's an extremely interesting process for me. It is maybe one of the first steps that we are taking towards automating scientific discovery. It is very primitive at this stage, but probably this is a very simple experiment that they could automate it. But you could imagine that if we keep going in the same direction, you're not going to be limited to biology anymore. We can do experiments that are more complex, hopefully, in near future in an automated way. So the cynic in you might ask, what is wrong with science? It is working fine, so why do we need to do anything about it? And the reality is that it is not. In 2016, there was 1.2 million biomedical sciences papers, and an average scientist reads around 250 papers a year. That's a clearly bad mismatch. So a lot of these papers that are generated are never read again. They just are generated and put up somewhere, and that's it. Everybody forgets about them. And that means that the quality of the research, the quality of scientific research that we are doing is declining, and a lot of research, a lot of results are not reproducible. And that's bad. That's bad for science. That's bad for us. And of course, part of the problem is that science workers, obviously read grad students, are human. They are prone to getting tired and making mistakes. And they're limited in their memory and computational power of their brain to imagine and capture all the available science to do things. And beyond that, as we go on, right now we are doing, for example, experiments in Antarctica, and that's an extremely harsh situation for us to be there. Imagine having robots that you send to Antarctica for a month, and it comes back with a bunch of papers without talking to you. And speaking of papers, maybe in this new world, we don't need to talk about scientific papers anymore. As I said, a representation of science can be a lot of concepts that exist in the form of a graph that are connected to each other. And maybe a new representation of the state of the science would be this new extensive data structure that represents the science, and scientific paper could be just a high-level abstraction of those concepts when we need them. I know a lot of what I'm saying sounds crazy, but I'm sure there is someone out there who's thinking about it and knows how to do it. We'll figure out how to do it eventually. Thanks, that's all.
Question. I'm just curious with this talk, because historically there were a lot of discoveries in mathematical methods, say, of interpretation being done in physics and then applied in other places, like black holes, for example, great example, in which the whole derivative pricing is there. Basically, these two guys met.
Right.
Physics rockstay and how to say thermodynamic equation result. So physics historical and physical education was historical as a place when people develop applied mathematical methods, and then these methods went into all these different areas of life, in economics, in finance, in biology, and a whole bunch of other things. Now, do you see this changing in terms of, if you are saying that and physical rules were developed this way, are you saying that now there are some other people who are developing these great things like neural nets and something like it, and basically physics, instead of a place where new ideas and new concepts are walking the data generated, will be just one of the other users? Because that like doesn't seem to be a good future then for physicists if it is this way. Or is it going to be that being faced with a bigger challenges like this, more complicated data sets that, for example, in CERN they have to see doing the experiments, we'll see big advances in deep learning and other techniques being coming out of physics and then again being used in other areas?
That's a very good question. I'm definitely not promoting the idea of physics or any other sciences being the consumers of deep learning, and I don't think that's going to happen. It's going to be, as you mentioned, like interaction of physics with all sciences has always been in a way that we consume some, but we also generate a lot. Like, as you said, we generated, like physicists, generated a lot of mathematical concepts and statistical concepts and things like that. And it's always going to be a two-way thing. Like, it's going to be, like, I wouldn't be surprised at all, like, if computer scientists can't really figure out how to decipher why deep learning works, but physicists can. So I don't think it's going to be anyone going out in favor of others, but it's going to be an interaction of all of these and having multidisciplinary fields, and especially with power of computation that we have and we're building, I could easily, not easily, but I could see a future where a lot of things are done in a computational way. And a lot of the limitations that we have now, like for example, we're generating science and we're keeping science in the form of scientific papers because that's the only way we know how to do it. But it is possible to imagine different ways to do it that might be more efficient. So yeah, I don't know if that answers your question, but I'm happy to chat more about it later.
Always when we talk about AI, always they talk about it like technologists or physicists or biologists, but I've never seen somebody talk about from an artificial, from real art point of view. We see like AI creates novel in Japan, paints a picture.
Definitely.
Somewhere else composes music.
Yep.
So AI is, I don't know, but I see that AI is going to be in a lot of other fields.
Definitely.
A lot of other people are going to have to be engaged into this because we are a few steps away from, we are already started what we call synthetic intelligence, and we are a few steps away from creating artificial consciousness.
Right.
So do you think that there are a lot of, I don't know, like societies are declining this way, or they're just rejecting us because they are afraid that it's going to take their places?
I'm sure a lot of physicists won't be happy with me saying these things here, but I think that's we cannot avoid it. It's going to happen one way or another. That's my opinion. But I think I have a very good spying device in my pocket, and I'm walking around with it. 10 years ago, I probably would have been very paranoid about it. But today, I'm happily carrying this around. I'm selling my data and all my privacy just because it is convenient, because it empowers me to do a lot more. So I can see Ray Kurzweil, I asked him a question very similar to that at a conference a couple of years ago. And I asked him, should we be worried about it? And his view that I adopted, that I really love, is that the most probable, at least short-term outcome of all of this is going to be AI augmenting us rather than replacing us. So especially in the creative parts like art, like science, that's probably not going to happen anytime soon. And I could see it helping us do a better job in whatever we are doing rather than replacing us. Someday it might replace scientists and artists and everything like that. But to me, that sounds very far. What I'm hoping to reach first is a state where we get a lot of advantage out of working with AI together.
Just to be clear, I
Mm-hmm.
didn't say it will.
Okay.
I'm still hopeful that it's not. I'm still hopeful that we're going to emerge sometime
Yeah.
and we'll work together.
Right.
But what I'm saying about, because a lot of people, including the governments,
Right.
a lot of governments around the world are not willing to engage because they are fear of doing that. Now, I don't believe that it's going to replace us at any time soon or maybe even ever. But it's going very slow sometimes because
Sure.
if you go to enterprise, they are very happy to do that and then just do things faster.
Yeah.
And but the private sector cannot be disconnected from enterprises
Mhm.
or semi-government,
Yeah.
government, and those sectors are still, when I talk to them, still very afraid of putting this and say we're going to lose jobs.
Right.
That's a political problem.
Sure.
Again. But,
Sure.
well, I don't see that. But the question is there any way that the society of AI, the technicians can talk to those people and tell them that it's not going to happen? I mean, from your own opinion, I'm not just saying that it's going to.
That's a very hard question. I'll leave that to others to answer. But my personal opinion is that you're absolutely right. We need more conversation about it. Somebody pointed out regulations that are coming up in Europe. Like, we need a lot more things like that. Yeah.
I'm not talking about that. I'm talking about North America, which is.
Yeah.
Thank you very much for giving the presentation and for raising the issue about the very large number of papers that no one reads. Yeah.
See a lot of people relate to that.
Sciences. So, do you have any ideas how this situation could be alleviated, say, in the future? I mean, some machine learning algorithms
Yeah.
that people should use
Mm-hmm.
to increase their knowledge of what's being done in this or that area, say physics or biology, say, for example, language processing of
Right.
abstract or something like that.
Definitely. Like, as I mentioned, I believe that the first step is AI augmenting us. I actually was talking about this talk with someone a few days ago who told me about a company called Meta here in Toronto, and what they're doing is exactly using like natural language processing and things like that to look into the papers that are generated to figure out, like, their purpose is at this point things like predicting emergent fields, for example, like the fields that are just about to take off. And obviously, that's a business to sell it to whoever is interested. But I could see things like that being more abundant and useful, and scientists can use them to do a better job. But the big problem is that as long as we have the academic system in which you have to put up a lot of papers to get anywhere, this problem is not going to be solved.
So actually, there was an archive paper that was mentioned earlier there, the on machine learning one. So archive is a place where lots of papers go because it's like you can freely browse them. There's that site, but then there's a search engine for it called Archive Sanity. It's ARXIV.
Yep.
Sanity by Under Copy. And basically, my understanding is that's using machine learning to find good papers.
Well,
Based on search criteria.
yeah. I was working on a project related to that when I saw that website. And what he's doing there is he's trying to build a sort of recommendation engine based on the papers that you liked before. So the problem, okay, you're bringing up a very good point, because I think one of the ways to solve that problem is open source in science. Like you shouldn't have to pay for scientific papers to see them. And a lot of people are talking about that now, and arXiv is a great example of doing that. But then the problem is that there is no filter. Like you see a lot of paper up there, and it's very hard to like weed out and find what is interesting. And Andrei's work is towards those lines, to like sort of rank the papers according to relevance to what you're interested in. But yeah, a combination of all of these is going to make it great again.
Well, you mentioned quantum computing. I know that it's not related directly to the talk, but I'm wondering, like as a physicist, does it make sense to work on things like quantum consciousness, for example? I mean, how seriously it can be taken?
Do you want my blunt answer, or?
Well, maybe some reasoning also. I mean, if you say it's no.
What do you mean by quantum? Okay, let
such a topic exists, right?
Sure, but that annoys me. Okay, let me. Okay, I can talk about consciousness for hours, but to me, consciousness is a very complex process that we haven't figured out. It's nothing magical. It's essentially an input-output system, and there might be quantum involved in it, but most probably no. But we don't really understand it enough to be able to say anything at this point. And I know that people are talking about it, but I honestly, it is way too blue sky for me now.
Just related to this question, do you think that quantum computation can be used to anything else than just to speed up, computation, just to have some quality coming out of it that's different to the classical computation? I think in all physics-related papers,
Yeah.
it's the only thing that is basically what you expected to get is a speed up.
Sure. Well, first of all, a speed up is a big deal. And it's not only a speed up, it is the scaling that would be different, in a sense that I feel like I'm going to give my quantum machine learning talk, but the reason that quantum computing is interesting is that the scaling is very different. For example, finding prime factors of a number is the reason that our communication is secure today. Because if we grab a really large integer, it's very difficult to crack it and break it down. But a quantum computer can do that in a linear time rather than exponential. And as you make it bigger and bigger, it just scales linearly. So, and that scaling is a big deal. Like, it is a speed up, but it's not just a factor. It is the scaling that is different. And that could open up a lot of, if it happens, I've worked on it for like many years, but at this point I'm slightly cynical. But if it happens, it's gonna provide a lot of possibilities. Like simulating complex systems like E. coli that I talked about briefly would probably be a lot easier on quantum computers rather than classical ones. But like something that is like magically different, I don't know. We just have to wait and see.
So thank you for the talk. My only question is, you mentioned this cycle of knowledge, like how do we generate results and theories? And there is one part that is experimental, like experimenting and stuff. How does machine can do the experiment?
Robots, baby.
Sorry?
Robots.
Like you mean the actual robots?
Actual robots.
But they have to have the input again, right?
That's right.
So the fact that it's an iterative process doesn't mean that the machine can easily do it over and over and over and fast enough, right? Because they also have to do the experiment.
Oh, for sure. Right. But the difference is, grad student works 16, 18 hours a day, 7 days a week. Machine can do it. That's right. Machine can do that 24/7 without much friction. So it can do a better job. And then after like 10, 12 hours, a grad student probably starts making mistakes.
Yeah, those are the, yeah, but like doing the experiment itself is a big deal. Right?
Sure, definitely. But yeah, 100%. But the thing is that the bottleneck is not, it is to some extent the experimental part, but a lot of the time ideations and coming up with new ideas also takes a lot of time. Like you go 6 months to come up with a new idea that is worth trying. But a machine that can just go through the cycle quickly doesn't even have to come up with the most brilliant ideas because it can just try them. Like it can't be like garbage at the beginning, but it can come up with like half decent ideas and quickly try them and feed it back and then keep doing that until it comes up with something that is interesting. So that I think is the difference. But you're absolutely right that you cannot really shorten the measurement times because that has to happen.
And in terms of reading the papers and stuff, I think IBM Watson does something similar to some extent, right? So it grabs the knowledge from different data sources
Right.
and generates some kind of logic out of it, right?
Sure. There are definitely a few, like LinkedIn has their knowledge graph, Google has their knowledge graph, Microsoft has something. I guess Maria can tell us about IBM more. But yeah, like it is underway.